Hello everyone, myself is Pragya Jain and my topic is energy management techniques for SOC design. One of the biggest problem in complicated and high performance SOC design is management of energy and power consumption. In this presentation, we present energy management techniques in system design including hardware and software SOC architecture and logic design. The contents of the presentation includes the following issues: power and energy consumption in SOC design, trade-off between energy and power performance, trade-off among energy, that is latency and computational precision, reliability and flexibility, techniques for reducing dynamic power consumption, and leakage power reduction techniques. Now, introduction. In past years, the most serious concern for the VLSI designer were performance, cost, and reliability. However, this paradigm has shifted. The driving factors of the paradigm shift include the following: popularization of portable electronic devices, raising demand for reliable and stable computer systems, worldwide environmental destruction. One of the biggest factors which motivate the need for low power SOC is the popularization of portable electronics. The second need for low power comes from a strong pressure for designer of high-speed products to reduce their temperature. Therefore, cooling down the chip temperature is essential for reliable and stable operation of computer systems. The leakage power issue makes this situation worse because the leakage power increases exponentially as the temperature of the chip increases. Worldwide environmental destruction drives the strong need for low power electronic devices. Recently, many energy reduction techniques at various levels of abstraction, such as at device, circuit layout, architecture, and software levels, are proposed. Dynamic power consumption is the major factor of energy consumption in the current CMOS digital circuits. The dynamic power consumption affected by supply voltage, load capacitance, switching activity. We present approaches to controlling supply voltage, load capacitance, and switching activity dynamically and statically in system architecture algorithms design levels. Now, the next topic is power and energy consumption in SOC. The energy consumption of a system E can be defined as the summation of both spatial and temporal power consumption of circuit. As the equation becomes total power is equal to dynamic power plus leakage power. Energy is the integration of the power, where P is the power consumption of the target system, P dynamic is the dynamic power consumption of the target system, P leakage is the leakage power consumption of the target system, and other are switching activity, load capacitance, operation voltage, where T is the execution time of an application program. We treat the energy consumption E as an objective function to be optimized because the energy consumption is closely related to the heat and reliability of chips, battery lifetime of portable devices, and the number of nuclear and gas turbine power stations required. The main approach is detecting a spatial and temporal hotspot and reducing the power consumption of the spot, since the power consumption dynamically changes according to the behavior of the software running on the chip. Both the software and hardware should be taken into account for reducing the energy consumption of a SOC chip. The key point of the energy reduction SOC design is considering design trade-offs among energy consumption, performance, computational quality, system reliability, and design flexibility. The goal is minimizing the energy consumption under the constraint of performance, computational quality, system reliability, and or design flexibility. Now, the techniques for reducing or lowering operating voltage. Since energy dissipation is quadratically proportional to supply voltage, lowering the VDT has a strong impact on the energy reduction. However, the following drawbacks should be taken into account: loss of compatibility to external voltage standards, performance degradation, and reliability issues. Basically, we have the following three ways for lowering the operating voltage without sacrificing the performance of the system. First one is parallelize tasks so that the performance does not degrade even in a low voltage operation. We refer this approach as static voltage scaling. The second one is use the maximum available supply voltage for gates on a critical path and use a lower supply voltage for the other gates. We refer this approach as multiple voltage assignment. lower the clock frequency and the operating voltage when the maximum performance is not needed. We refer this approach as dynamic voltage scaling. However, it becomes more difficult in future to control supply voltage due to reliability issue. Breakthrough will be appeared if we can tolerate negative effects of process variations, temperature variations, soft errors and noises even in ultra low voltage operation. Thank you.